At UW-Platteville, we had a survey course that was given to freshmen in computer science that introduced them to the various different faculty members and also the various different topics that they might be interested in as either electives or um, to put their studies in the right order in order to get, for example, the computer networking course after they did a lot of uh, other binary things first. So this talk is a cow-themed seminar in Wisconsin, University of Wisconsin-Platteville. And the star of this talk is Fab Beef. It's a 32-bit quantity, 4 bits for each hexadecimal character. The way you can tell in most cryptography, you want to check when you decrypt something, you'll get a pile of bits, which may or may not make sense. If it ends with Fab Beef, then that's my marker that tells you that you have correctly decrypted and that anything that a correct decryption would prove is you can be confident of. The talk is entitled Secret Math, not because any of the math is actually secret. It's math that you use for talking in public about things that are secret. So let's get on and learn more about secrets, imposters, intruders, encryption, a little bit of discrete math in that course. So we're going to start with talking about the math that you do in order to have private conversations over a public medium. The picture you're seeing here is an unmanned underwater vehicle. This happens to be one that the Neptune is a Ukrainian unmanned underwater vehicle, and of necessity, it has to transmit and receive over the open airwaves. The enemy could hear anything you said. If it's very well encrypted, they might not be able to understand what you said, but they'll be able to tell that you were saying something. In the course of this 52 minutes, we're going to talk a little bit about the discrete math that you need to have in order to do encryption, how to and why you would encrypt messages, why you would sign a message, and we'll touch on what a digital certificate is. You'll get much, much more about digital certificates when we go into the network management course. So this is a Ukrainian R-360 Neptune missile. Neptune, missile, unmanned aerial vehicle. I don't want to confuse the difference between an unmanned aerial vehicle and an unmanned underwater vehicle. The event that happened in 2023 was the sinking of the Moskov. The Moskov was the flagship of the Russian Navy fleet, Black Sea Fleet. What happened in 2023 was that it was attacked successfully by 2 Ukrainian Neptune-guided missiles, possibly with the aid of some secret math, possibly with the aid of some unmanned aerial vehicles that used other weaponry first before the 2 Ukrainian Neptune-guided missiles hit it. Military analysts would have told you that this was not realistic. Sending 2 guided missiles against this particular frigate would be a senseless waste of two missiles that have wonderful artificial intelligence, wonderful optical vision systems, um, pretty expensive compared to other unmanned aerial vehicles, but insufficient. The Moscow is itself a guided missile frigate. It's perfectly capable of detecting and uh, tracking and destroying 12 incoming cruise class missiles simultaneously. Uh, if you shoot two missiles at it, it's capable of defending itself against 12 missiles. They'll just shoot them out of the air, and you will have accomplished nothing and wasted two missiles. So let's get some help. We're going to get some help from from an autonomous underwater vehicle. These things are inexpensive. They're often used for mapping the floor of the Black Sea. They're used for intelligence and surveillance and reconnaissance. And these things, little cigar-shaped thing, can very, very quietly shadow a guided missile frigate like the Moscow for days. They require very little power. It's not like an unmanned aerial vehicle that has to stay in the air. It's all it needs to do is float along at a reasonably slow speed, and it can even use solar panels to recharge batteries. It's battery driven. Imagine that you have a lot of artificial intelligence and some secret math. The good news is you can listen to all sorts of things that the other people are saying. The bad news is that they can listen to everything you say. So we're going to have to find a way to encrypt it. The clock on the wall, your clock on the wall, is really an introduction to what is modulo 12. If something takes 25 hours to do, and you start it at 1, you look at the clock when you're done, it'll say 2. The good news is, you and I can both do addition, we'll both come up with the same answer. We can do subtraction, we'll both come up with the same answer. We can do multiplication. You can take a task that takes 25 hours, do it 3,615 times, and I can tell you what the clock will say when you finish modulo 12. You can't do division. If I tell you I started to do something, I don't know how many times I did it, but when I ended, the clock said 2. You don't know how many days it was, weeks, months, years. So division doesn't work. So
Similarly, if I know something takes 10, if I know I did something 10 times, I can't tell you how long it took each iteration.
Right.
It's the other way to do division.
Yeah, it's the other way to do division. So that's a one-way trapdoor algorithm. We'll get to more sophisticated one-way trapdoor algorithms in a minute, but the idea is that if we add, subtract, or multiply, that's deterministic. You and I will both, if we take the same inputs, we will both always come up with bit for bit identically the same outcome, the same output. If we do division, we will not, because there's multiple possible outcomes, all of which are equally probable, all of which would result from the same division. And that's sort of the magic of using modulus arithmetic. We're going to use it with some really big numbers. So the math itself is openly taught in Kiev, Prague, Darmstadt, Germany, Platteville in Wisconsin, and I hope I spelled Worcester right. Is that the way you spell Worcester?
I think so. Worcester.
So all of the, Worcester, thank you. So all of the math that you use to do the encryption and decryption, I could put on a billboard along the highway. I don't care if anybody knows, everyone knows.
On a T-shirt.
Yeah, I could put it on a T-shirt, but it would be illegal to wear it in France. No, not anymore, but it would have been at one time where encryption was illegal. What makes it secret? What makes it so that I can tell secrets using this math? And the answer is keys. So we're going to talk about two different kinds of keys. We're going to talk about authentication. So I can prove that this message could only have come from me. We're going to talk about trust. I can prove that somebody who trusts me is also trusted by you. Talk about privacy. I can send a message that can only be understood by the intended recipient. It's gobbledygook to anybody else. And then we're actually going to flip hats for a minute. In the last half of the talk, we're not going to be white hats anymore. White hats are the people who do the encryption and the decryption. Black hats have the job of trying to figure out how to decrypt something when they weren't supposed to. So we're actually going to study what you have to study if you're a white hat. You have to study what do black hats do in order to figure out how do I thwart that? How do I combat that? So we'll do a little bit of the man-in-the-middle attack. We'll do a little bit of the replay attack. And we'll talk about just plain old ordinary eavesdropping. How can we make it so that they won't understand what we're saying? The background for this, the purpose of the example we're going to use to show you encryption and decryption is the Moscow. So this is the largest warship to be sunk in combat since World War II. This happened right near the Odessa. The Crimean Peninsula is Russian-controlled, and a big chunk of southern Ukraine is still, as of this recording, under Russian control. The flagship of the Black Sea Fleet of the Russian Navy was sunk by two Ukrainian cruise missiles. They used their artificial intelligence and their vision systems to recognize when they saw the Moscow, because they had a picture of exactly what the Moscow looked like, and aim, because they're guided missiles. They can change direction. They can actually linger in a circle. They can communicate with other cruise missiles so that they can coordinate to attack at the same moment, plus or minus a fraction of a second, and hit within a few feet, perhaps as little as 2, the exact spot on the Moscow where it is most vulnerable and where you're most likely to set the Moscow on fire. On the day that it was sunk, the Moscow was hit by these two guided missiles right at the exact perfect spot, started on fire. The crew couldn't stop the fire. The ship sank. Nothing on the ship shot at the incoming missiles, even though it has antennas in its sonar dome whose job it is to detect and track and get ready to shoot down the incoming missiles. Didn't happen. Didn't defend itself. So somehow those two incoming Neptune missiles were told something by somebody that said, go ahead and do it. Go ahead and attack it right now. How'd they do that? We're going to break cryptography down into two halves. There's symmetric key cryptography, and then there's asymmetric key cryptography. Symmetric key cryptography is that you start with some shared secret. So Ash and Bob have to know each other ahead of time, and they have to use some mechanism for sharing some secret that they do not tell the outside world. Then they're going to use that to encrypt a message. Well, you want the message to look really random. On average, over a long period of time, the message should have about half of the bits lit and about half of the bits off. Half zeros, half ones. And a good random number generator, that's one of the requirements of a good random number generator. Another requirement of a good random number generator is that for a very long sequence, billions of octets, billions of bytes, billions of characters, there should not be a noticeable repetition, because repetition would make it much easier for black hats to decrypt, to find patterns and then...
And it's deterministic, so once it starts repeating, it's going to keep repeating.
Correct. The algorithm that we're going to use for generating these, so they're typically called, in gaming, they're typically called the RNG. If you've ever been gaming online, you'll see people whining and complaining about the RNG. They're not actually correct about that usually. Usually they're whining about the random number generator because they didn't get the shield or the sword that they were hoping would drop from this particular mob. But usually those are actually pseudo-random number generators. If I start with a seed and you start with a seed and we're only using deterministic math, then you and I will generate the first octet. It's going to look like a random number because it also has to satisfy all the requirements of an RNG. A pseudo RNG has to have the additional requirement that if you start with the same seed, you'll end up with exactly the same very, very long sequence with no repetitions within that billions of characters, no big chunks of repetition, and that the numbers that come out will be indistinguishable from completely random numbers. Just garbage. We're going to use exclusive OR. The war in Ukraine is the U.S., which has some secrets, the UN, and people who use the word secret and the word UN in the same sentence are, and this is an inclusive OR, they're either fools or diplomats. Once you tell a secret to the UN is Swiss cheese with respect to keeping secrets. So that's an inclusive OR. You're either a fool or a diplomat, or both. Exclusive OR means that you're either soaking wet from the rain, or you're not, but you're not both. So exclusive OR is you're either A or B, but not both.
And not neither.
And not what?
Neither.
And not neither. Correct. So there are two possible outcomes that are 0, two possible outcomes that are 1s, and if I do a lot of addition, multiplication, division, which we will actually make use of, exponentiation, that if I started with a big long sequence that has about half 1s and about half 0s, I'll end up with a big long sequence that has about half 1s and about half 0s. If I did ands or ors, inclusive ors, then slowly I would end up with, in the case of an inclusive OR, I'm ORing 0 or 1 comes out to be 1, 1 or 0 comes out to be 1, 1 or 1 comes out to be 1 in inclusive OR. You'll end up with a lot more 1s than 0s, and then you perform some more operations and you get even more ones and even fewer zeros. And so it's not very good for doing encryption. So this is symmetric key cryptography. That means that I'm going to use the shared secret to do the encryption, and you're going to use exactly the same shared secret and exactly the same exclusive OR technique to undo the bit flipping that I did. And to see this, you're going to have to watch it in action. Be careful because symmetric key cryptography is so fast that you can encrypt movies, you can encrypt songs, you can encrypt telephone calls, because once you've got this pseudo-random number generator started, you and I will both come up with exactly the same very long sequence of pseudo-random numbers. I told you that we were going to start with some shared secret, and I want to introduce two-factor authentication here because whenever we start talking about encryption, identity, whenever we talk about trust, I want to make sure that we really are confident that that person is who they claim to be. So I believe that passwords that can be learned or remembered by a human being, I don't care how long they are insecure by my way of thinking. That you're much better off, rather than relying on a particular technique, keeping a secret. I want you to use two-factor authentication. Here's an example. I have an authenticator. You'll use these authenticators with everything from Steam to World of Warcraft.
MIT fobs for doing two-factor authentication inside the Kerberos network.
Yeah, inside Kerberos at MIT. Well, not just at MIT, but yeah.
Sarah carries one.
Really?
I believe so.
You push the button, and it gives you a 6-digit number. The server can come up with the 10 previous and the 10 future, just in case the clocks are a little bit off, and check to make sure that you've taken the secret, appended this 6-digit number to the end of that secret, hashed that. We'll talk about hashing later on in a few places. And you'll come up with, the server will be able to authenticate that you didn't just have the password, you also had something you have, something you are, or something you know. So you want two of those things. There's actually an entire section on what are the, out of two-factor authentication, there's really 4 kinds of places where you can get, and this is content for your key. And if you're getting your content for your key from 2 different places, two-factor authentication, it's much, much safer than you present a credit card at the pizza parlor and they give you a pizza. If you have two-factor authentication, you also should know the PIN that goes with that credit card. Chip and PIN. So chip and PIN is the classic example of two-factor authentication. How do you use this in real life? Well, here's the question. Why do milking stools have only 3 legs? Why do milking stools have only 3 legs? If we took some seed, and you and I both have this shared secret that we started out with, back when we were in the same room, that's going to be the beginning working storage, and we'll show it in the first row as working storage. If we crunch that, I'll say hash it, we'll come up with a very short 1 byte, 1 character random number. This is the pseudo random number in hex. The plain text that we want to encrypt is going to be capital C,
Yep.
which, as it turns out, is in hex 43. I'm going to flip the bits that are the B8 bits on that first row that starts with 97. I'm going to flip the bits that are B8. That makes ciphertext of FB. So what any eavesdropper is going to overhear is the ciphertext.
And the way you got bits to flip is XORing the plain hex with the hex random.
Correct.
Yeah.
Yes, that's exactly right. The bits to flip are the hex random, and the ciphertext is the exclusive OR of the plain text and the bits to flip.
Thank you.
On average, about half of the bits are going to get flipped, because that was one of the requirements of the random number generator, pseudo-random number generator. We're going to avoid 0 because 0 is a special case. So it turns out that we will never allow the hex random to be 0, but that's the only thing we won't allow. The eavesdropper overhears the ciphertext, which is complete gobbledygook. There's no discernible pattern to it, and there's no way for him to figure out, the black hat to figure out which bits to flip back. But the intended recipient started with the same seed, came up with the same hex random. He simply takes the B8, flips those bits back again. That's what exclusive OR does. And out comes the capital C. So the message he listens to, the message he hears is cow has the udder, and the message the eavesdropper hears is the ciphertext, the column that is 2 in from the right. Exclusive OR, I said it's extremely... White milking stools have only 3 legs. Cow has the udder. I apologize for cow-based puns, of which there are several. I did want to tell you that an exclusive OR is a very small number of transistors, and that this operation, in order to do a movie that is 4 billion characters long, 4 billion bytes long, you simply have to run the pseudo-random number generator one more time to get the next octet, and then do the exclusive OR, transmit that. The recipient just has to do the pseudo-random number generator to get the next bits to flip, exclusive OR that back. So it's so symmetric key cryptography is ridiculously fast, ridiculously cheap.
Way cheaper than addition.
As it turns out, it's actually way cheaper than addition. That's right. With addition, a half adder is just a couple of transistors, but there's a carry bit. So if I add 1 to 1, I'll end up getting 0, but I have to add a carry bit for the next higher bit. So if I was adding 9 and 1, I have to ripple the carry. And in terms of how many transistors it takes to do that, it's significantly more than just a simple exclusive OR. It's still only 1 clock tick. And I'll tell you that in modern times, a clock tick is usually smaller than a nanosecond, because your phone that you carry in your pocket is running at 2 gigahertz or so, and your computer is probably running at 4 gigahertz with multiple cores and multiple threads per core. So the number of instructions that you can get done is in a single second is billions, several billion instructions per second. And so exclusive OR, very, very inexpensive. Symmetric cryptography works okay as long as you can start with some shared secret. But what if you can't start with a shared secret? What if you're an unmanned underwater vehicle and you desperately want to tell an unmanned aerial vehicle that you've just seen some behavior in the Moskav, the flagship of the Russian Army Black Sea Fleet, Russian Navy Black Sea Fleet, that it is exhibiting a behavior right now that is characteristic of being blind and deaf. You're an unmanned underwater vehicle. You can't just beam a transmission that only goes to just exactly the one unmanned aerial vehicle that you want to tell this to. You're going to send a transmission to the open airwaves. Who knows where that's going to go? Black hats all over the place can hear that. The guy you're sending it to may not be somebody that you have previously agreed to. I have these 7,000 keys because for each good guy I want to talk to, I would have to have some shared secret with that exact good guy.
Mm-hmm.
And that's not practical.
Mm-hmm.
PKI, public key infrastructure, has to do with keeping a set of public keys. And you'll study the RSA algorithm, which is the classic example of public key infrastructure where you don't have just one symmetric key that you're using for both sides. It's asymmetric cryptography in the following way. You encrypt something using either a public key or a private key. I'm going to think of that as being 7.
Okay.
You can't use that key to decrypt it. You have to use its inverse. So there's another number that in this modulus is the inverse of that number 7. It will undo the effect of multiplying something by 7. You're going to multiply it by 1/7, and poof, you started out with fab beef. You encrypted. You came up with ciphertext that is opaque. And when you use the opposite key, you'll get back exactly fab beef, bit for bit identical. In asymmetric cryptography, knowing the public key gives you no clue as to what the private key is. It is computationally inconceivable that anybody could take a public key, which contains a modulus and a very, very big number. We're going to be dealing here with numbers that are in the quintillions easily. And then real cryptography is numbers that are much, much bigger than that. So it's computationally infeasible to even bother to try to figure out what the private key is. You could take and do a plain text attack. Imagine that you know what the plain text of a message is, or you can guess it, and you know what that message is when it's encrypted because you overheard it. Can you use that attack to try and figure out what the private key is?
The Nazis in World War II ended many of their messages with Heil Hitler, and then encrypted all of their messages. And that was one of the ways that Enigma was broken.
One of the ways that comment, I don't know if you heard the comment, I'll repeat it. World War II, Enigma encrypted a bunch of messages, but the submariners who would come to the surface and transmit a preamble, the time, the weather. They wanted to know the weather in the Atlantic Ocean because that was a very good predictor of the weather in the English Channel. And they needed to know what the weather was going to be like in the English Channel because it was dangerous and senseless to send a whole bunch of aircraft across in bad weather. They wanted to know the weather. And the weather forecasters said, we have all these submarines in the Atlantic Ocean. This is a wonderful way to predict to do weather analysis and prediction. And every hour, not exactly on the hour, but different for every submarine, they would all transmit a thing that was in a format that was pretty easy to guess. And Alan Turing, the father of modern computing, arguably created things that were the precursors to the first computers. At Bletchley Park, created a machine that could figure out the settings on the dials on the Enigma machine, which told you how to decrypt the messages that the U-boats were sending. Interestingly enough, they couldn't use the information because if they told the Germans that, or if they did something that proved that they had intercepted the German messages, then the Germans would have changed the Enigma machine and added another dial, which eventually they did do. But the British had to create a unicorn team. Unicorn team is made up of one person who understands the real actual technology that exists. And the rest of the people on the team, typically 5 or 6 other people, were really smart, but intentionally did not know about Enigma machines or how to crack any of those codes. And they were told, you must come up with a plausible story for how we know where those submarines were so that we knew not to have the shipping lanes populated with a bunch of ships that were coming over with things that we wanted to have in England in order to survive, food and tanks and things. Um, then, by various means of subterfuge, uh, in very similar ways to the way they subsequently convinced Germany that the attack on D-Day was not going to happen at Normandy, it was going to happen at Calais. They convinced the Germans that the attacks in Sicily were not going to happen in Sicily, they were going to happen in Greece. And they used all sorts of mechanisms for making it so the Germans believed that they had discovered some deep, deep, dark secret, when in fact what they actually discovered was disinformation, intentionally given to them. So the Unicorn team came up with the idea, we have these special infrared cameras that can see the submarines when they're either um, descending but they're not far enough down yet, or we can see the submarines. The Germans actually called all of their submarines back from where they were and painted them with special paint that would mimic the infrared characteristics of the seafloor. Um, because they were convinced that the reason the Allies knew about the submarines, where the submarines were, was because they could see them with these special unicorn. Completely mythical technology didn't exist. Disinformation. Public key, private key. Um, I wanted to tell you that the credit card you carry in your wallet has a private key. It will never tell anyone it's a private key. In fact, it's not even capable of getting it out to the outside world. The credit card gets challenged through its chip with a random number and uses the public key that the credit card will happily tell you. Credit card contains a certificate, we'll talk about that in a minute, that proves that that credit card authentically came from Worcester Bank. So this credit card says, I'm trusted by Worcester Bank, and the point of sale machine says, if that's really true, then you can give me back what's the random number that goes with this encryption that's encrypted using the thing that you told me was your public key. The reason that we can trust that is in fact that credit card's public key is because the certificate signed by Worcester Bank says, and oh, incidentally, this credit card's public key is this. It's his public key. I will tell anybody my public key. The only way to decrypt something that's been encrypted with my public key is to use my private key. The credit card knows its private key. It decrypts it, comes up with the random number, and tells the point of sale terminal your random number was 123456. So keep in mind that that's how public keys and private keys work. They're the inverse of each other. And in PKI, when we talk about network security, will actually tell you how to come up with two massive numbers which have this magical property that they are the inverse of each other under that modulus. The modulus also being another massive number. I told you that there's a digital certificate. In this example, the unmanned underwater vehicle, which is unremarkable. It's very quiet. You'll be very difficult to detect that unmanned underwater vehicle's been shadowing Moscow for days, maybe months, because it doesn't have humans. It doesn't need air. It doesn't need anything. It doesn't run out of food. So the unmanned underwater vehicle has a cert that was signed by the Navy.
Okay.
That cert is unique to that particular unmanned underwater vehicle, and it tells anybody, here's the public key of this unmanned underwater vehicle. If you encrypt something using this public key, then this unmanned underwater vehicle can survive that challenge. He can decrypt it and tell you what the decrypted random number is.
Okay.
Okay? So the certificate is itself signed then by the higher authority. So I'm trusted by some higher authority. You trust that higher authority. Between the two of us, I can send you a message without having had this prearranged shared secret. We don't have to have a shared secret. This is helped if you have a database of all the public keys. So if you have a database that has just the public keys for the big guys, you got a public key for Worcester Bank, then anybody can check and see. If I have to, I could challenge Worcester Bank and say, do you own the private key that goes with this public key? He can prove that that's his public key. And now I can prove that I'm trusted by Worcester Bank. And that's what digital certificates are for. They're just to provide you with a public key that's not one of the ones that's in the public database. Because the public database doesn't have billions and billions of keys. It only has millions and millions of keys, merely. And there are several public databases, and I don't understand why 2 decades later, after this technology was written down in this middle column, the middle column is given what you know, how do you develop something from a random number that you can encrypt, that only your intended recipient can decrypt. So the challenger can verify that the decryption of the encryption of the random number using the private key using the public key matches the random number. I successfully matched the random number that I used to generate my challenge, and when the intended recipient replied, he told me the random number. So he proved he can decrypt it. He proves that he is who he claims to be, and that's crucially important. It also gives you non-repudiation, but we won't get into that in this talk. I wanted to get a little bit deeper into some of the number theory, just to tell you that we flip a bunch of bits. We typically hope that we're going to flip about half the bits. What we're trying to gain here is two things, a little bit of confusion and a little bit of diffusion. And all the early cipher techniques, so a Caesar cipher, is that you take a letter and you replace it with some other letter. A common use of a cipher like that has lots of confusion but no diffusion. A Caesar cipher, if you can crack a piece of it, then you can figure out, just like a cryptogram in the newspaper, you can figure out that R means F and G means Q, and pretty soon you can cobble together the message that was intended. Rot 13 we used to use if you had a spoiler. So you're playing a game and somebody asks a question, but the answer to the question would have been a spoiler. So rather than give the spoiler in plain text, we just use Rot 13. Rot 13 is a very simple algorithm. Every time there's a letter of the alphabet, you simply use the letter of the alphabet that's 13 away from it. So E becomes R, R becomes E. If you're looking at the spoiler, you won't immediately recognize the hint or the clue that you're supposed to that you wanted, that was the answer to your question. But somebody who didn't want the spoiler is just going to see something that kind of looks like gobbledygook. Well, it sort of does. It's got good confusion, so it results in about half of the bits lit and about half of the bits off. But it doesn't have good diffusion. What you really need, so that you can avoid people seeing patterns. The word "the" is pretty common. A column of numbers is going to have digits and commas. And
Hello has two L's in a row.
yeah, hello has two L's in a row. And if they both, in Rot 13, L would translate to Y. And in the, I'll call it ciphertext, it's not very good ciphertext, you'd see two Y's in a row and you'd say, oh, well, that's two letters that are the same. And pretty quickly you'd realize that hello was one of that kind of fits in this place in this sentence, and now you're one step closer to decrypting the entire message. So diffusion is that we're going to try and find ways to encrypt such that if you change any bit anywhere in the entire message, about half of all of the ciphertext bits, and in this case I'm actually going to say even the ones that came before that in the message, are going to flip. So a message that has even a single bit flipped or changed in the message, don't give Wilma a raise. Changing it to give Wilma a raise would change, hopefully, if the encryption has good diffusion, it'll change so many bits in the ciphertext that it's a massive change in the ciphertext, and it's okay if the plain text has lots of patterns in it, because they will not show up in the ciphertext.
Okay.
They're not patterns in the ciphertext. Take a step back for a second. What good would it do to tell secrets to the unmanned aerial vehicles, these Neptune missiles that are lingering in the air, waiting to attack the Moscow?
Okay.
What good would it do to tell them anything? And I'm gonna claim that there's a secret that you really don't want the world to know about. That EMP, when you set off a hydrogen bomb, there's going to be an EMP. It's an electromagnetic pulse, and it attacks antennas. It creates a massive surge in any antenna of any kind, and it'll burn out the things that the antennas are connected to. You just burn them right out. It's like a lightning strike. Could you do that without having to have a nuclear bomb? Nuclear bombs are pretty messy. And it's hard to make a small one, actually. So a non-nuclear electromagnetic pulse is a weapon-generated, silent, invisible attack on a ship, an airplane, a guided missile. This example shows a Champ missile. The Champ missile can carry a payload of bombs, but it's also designed to be able to handle to be able to create a non-nuclear electromagnetic pulse. And there's a couple of big secrets involved here. How close do you have to be for that to work? Because if you're not close enough, you've got a focused electromagnetic pulse, but it's not focused enough to completely burn out things that are well shielded and hardened against non-nuclear electromagnetic pulse. And the good news is that most of the chips that do um, the sensing, you take a signal that comes from an antenna, and you detect is there any big piece of metal that's reflecting um, these rays. Um, so I want to stick out an antenna, shoot out some radar, and see what comes back. Well, that's an antenna. How close do I have to be to burn out the thing behind the antenna using this non-nuclear electromagnetic pulse? So a lot of times, Iranian planes, Chinese planes, missiles, rowboats would come within 75 feet of vessels in order to test and see. Well, I would argue, I'm speculating here, they weren't just being show-offs. They were testing to see whether or not can we burn out their stuff using our. We bought this non-nuclear EMP from some guy who claims that it could make this kind of a frigate be blind and deaf. What? Blind and deaf? What's that? Um, we'll get to that in just a minute. First, I want to get a little bit further along in the math. I told you that we could encrypt things using exclusive OR. But I also want to at least introduce what a hash is so that if you haven't heard what a hash is, imagine that message digest like an MD5 is just like keeping just the last teaspoonful of the output when you ran this complicated mathematical set of operations on fab beef, and you came out with something much, much smaller than having 4 gigabyte encrypted movie. Yeah, you end up with just a hash, a very short thing that is a message digest. So MD5 is the typical kind of specialized type of hash, but it's a good example of take something big and you come up with something small, but which for any single bit change anywhere in the entire content payload, the resulting MD5 is going to be unrecognizably different in lots and lots of bits spread out throughout. It has good.
It's like a checksum bit, except it's not just a single bit.
Right. The good example of that one is CRC, a cyclic redundancy check compared to a parity bit. A parity bit is a very simple way to have error detection, but not error correction. But if you do longitudinal parity along with parity, so you have 2 dimensions of parity, then you get error detection because the content did not match the parity bit. It's an odd parity, then for every row, there's going to be an odd number of bits lit. The parity bit is not used for data. It's just used for error detection.
Yep.
But it's the same true for columns. So now I've got a bit at the bottom of each column that is just purposely made to make it so there's odd parity in each column as well. And that gives me the ability to do single bit error correction. I can take something that came out wrong, and the error detection circuit is going to say, that's wrong. There are parity bits that are wrong, that don't match. You've lost a bit somewhere. Either that wall was a little thicker than you thought it was. That frequency had somebody turned on a compressor. Your car engine had ignition glitch. Um, you, in transmitting things over long distances, over frequencies that are just barely can make it that far anyway, you're going to miss some bits. Sometimes in Wi-Fi, you'll lose a lot of bits, but we have lots of ways that we're going to do error correction. So when a CD with music on it is burned, it's got error detection and error correction. When a DVD is burned, about 40% of the surface of the DVD is used up in error detection and error correction so that you'll be totally unaware of the fact that that DVD has defects. They were either there when the DVD was manufactured, or it's been worn out, or scratched, or for whatever reason there's bits missing in a lot of places. But the error detection realizes it. You use the error correction. So I told you that story to tell you this one. There's a reason for us to be interested in message digest and message digest 5 hashes. Here's the motivation. 2016, the U.S. Navy had an unmanned underwater vehicle. The U.S. Navy Bowditch was supposed to retrieve that, do some repairs, put it back in the water. Unmanned underwater vehicles don't need a lot of attention. These are autonomous underwater vehicles. They have a lot of artificial intelligence in them, but you do not want them to transmit very often because they'll give away their position when they do. So the U.S. diplomats said, well, this autonomous underwater vehicle is really just gathering weather and temperature data, and it's mapping the floor of the South China Sea. Well, a Chinese warship interposed itself between the Bowditch and the autonomous underwater vehicle and stole it, literally stole it. And they kept it for a couple of weeks, and then the diplomats on both sides yelled and screamed and came up with lots of reasons why this is a completely peaceful drone. No humans were hurt. Let's just give us back the drone, and we'll be completely happy. When it came back, it may not have. It was returned several days later. It may not have weighed quite as much as it weighed when they first intercepted it. We don't know. But it certainly had, as it turns out, a lot of technology in it that was not for gathering weather and temperature data. And the secret of how it did what it did and what it did was probably compromised. Here's where it happened. This is an area of the South China Sea that is disputed. China made some islands in the South China Sea, and they claim that is therefore that their international waters are not international waters. They're Chinese waters now. And the U.S. says, no, those are still international waters. That's where this happened. Sonar Dome is the place where all these delicate electronic circuits are kept. The sonar dome is where they send out the sonar and they analyze the return from the sonar in order to figure out where is the floor, to map the floor, but they're also trying to figure out where is the enemy, what is the enemy saying. So this picture shows the USS San Francisco, which was dry docked in order to make repairs to the sonar dome after and here I'm gonna take a little bit of a leap, and I'm gonna say the USS San Francisco was dry docked because it had suddenly become blind and deaf inexplicably. And when they made the repairs, they replaced the steel dome with a much thicker, much more hardened steel dome on their sonar dome. It's not the only time it ever happened. I'll give another example from the UK, and as you can clearly see, the UK spell the word defense differently than we do. In 2008, this is a British nuclear-powered submarine damaged after it, they said, hit rocks. It's really, really unlikely that it hit rocks because A, it's very good at mapping the seafloor on its own, and B, it contains a database that is accurate to small number of feet for where the seafloor is at any moment, and the damage to its sonar equipment forced it to surface, go back to port to be repaired. A more recent example, in 2021, this is the USS Connecticut, which had to go back to port. It's a fast attack submarine, USS Connecticut, smacked into an undersea mountain. This was a Seawolf class fast attack submarine that had ludicrously accurate map of what the seafloor looked like, and equipment that would detect how far away it was to the seafloor all the time. But it smacked into an undersea mountain, according to the diplomats, according to the Navy. And incidentally, it also had to replace all the equipment in the sonar dome. Right. Just a coincidence. So we want to send a message that we think the Moscow is blind and deaf. Here we are, shadowing the Moscow. It's just done some things that we think are behavior that's consistent with it being blind and deaf. We would like to tell the unmanned aerial drone that is Ukrainian. We're forced because of the diplomats. Anything we tell to Ukrainians, we have to tell to the UN as well. That's one of those requirements. So we'll get to that in a minute. But the technology we're going to use here is that we're going to prove to some completely unknown thing, this unmanned aerial aircraft, unmanned aerial vehicle, we're going to prove to them that that we know a particular secret, a particular word, a particular... I'll use a password as an example. Again, I think passwords that are 8 characters long and contain exactly this punctuation and this number of digits, and I think that's all, to be honest, a complete anachronism that has nothing to do with real actual security. For real actual security, you're going to need 256 bits worth of randomness, and it's going to have to be or more. And you'll see that we typically do. For this example, I'm going to pretend that we're only just using 64 bits of randomness. Mm-hmm. So, Ash would like to talk to Bob. How do we know, how does Bob know that he can trust that Ash is, knows the password? Mm-hmm. Well, you can't just transmit the password. That would be just stupid. Anyone would know the password. But you can take a random number and concatenate it to the end of your password. And I told you that when you hash a big long thing, you end up with something short, and that if there are any changes in the big long thing, the hash will come out very different, even if it comes out any different at all. So I attach the random number to the end of the password, and I can actually tell the other side, and here's the random number. They can take, if they know my password, they can take what they know to be my password, add the random number to that, hash that, If they come up with the same answer, they hash it and it comes out to be the same, then that means I know my password. The important point here is that I proved I know my password without having to say it over the air on public airway. I'm not even giving you anything that encrypts or decrypts to my password. Okay? In reality, it turns out that the details of how that password authentication works, it varies a little bit depending on whether you're logging into Microsoft Active Directory or Novell file servers. But the important point is that if the values match, it wasn't a lucky guess. In this example, one chance in 64 bits is one chance in 2 to the 64th. That's roughly 6 commas, all the zeros you need to put in between those things, and preceded by a 16. That's because we'll get into more of this when we talk about large numbers. 2 to the 64th is 2 to the 10th times 2 to the 10th times 2 to the 10th, 2 to the 10th, 2 to the 10th, 2 to the 10th, times 2 to the 4th. Because 10 plus 10 plus 10 plus 10 plus 4 is 64.
Plus a little.
Yeah, well, in this classroom, 2 to the 10th is 10 to the 3rd, which is a comma. So when you're multiplying a number that's got 3 commas times a number that's got 4 commas, you're not going to care very much about the 24 on the end. Right? And that's what you have to do if you're going to send a new copy of some game that's got you only changed a gigabyte worth of stuff in the game, but you have to transmit it to 10 million people who own the game. So you now have to transmit to 10 million people 1 billion characters. It's a lot of characters. So we take numbers that have 3 commas and we multiply them times numbers that have 4 commas, and we end up with numbers that have 7 commas.
Yep.
That's just, let's not worry about the 24 on the end. 1024 is basically as close enough to a comma. Incidentally, I think it's important that we should pronounce commas. So when you see a comma, I want you to think of that as pronounce it. And so 16 quintillion is 16 followed by 6 followed by all the zeros that you need to fill in the middle. Just, numbers on the other side of the decimal point. In this country, use a decimal point to separate whole numbers from parts of a whole number. And it's not good to talk about it in discrete math, but there actually are numbers that are between 3 and 4. In discrete math, there aren't. But we'll let you have fractions in other courses. I don't like the fact that they sometimes put in nanometers or in picoseconds, they sometimes put a whole bunch of zeros and then a digit or two. And it's really hard to count all those zeros to try and figure out, is that nanometers or is that micrometers? Yeah. So I want you to put commas also on the other side of the decimal point as well. So 10 to the minus third, 10 to the minus 6th, 10 to the minus 9th. Anyway, that's actually not a number that's anywhere near big enough. The 16 quintillion, MD5 I told you about earlier as a hash, it's actually 128 bits. It's twice as many bits as this. So take 16 quintillion and square it. And that's how big 128 bits is. SHA 256 is 256 bits, and that's 128 bits squared. Just so you know, we're dealing with some pretty big numbers here. Get comfortable with big numbers, that's going to happen. I'm going to make it a little bit simpler just so that you get a sense of what the black hats are going to do. So white hats, could take and generate a commodity called, I'll call it E1 here just for nomenclature, that's the MD5 of my password. Because you can't, it's a one-way trapdoor algorithm, you can't take the MD5 and figure out what the password was, given that it's got this hash. The hash is not as an irreversible process. It's computationally inconceivable that you could figure out what the password was given just the MD5 of the password. But you don't have to. If I tell you I would like to get this file from this file server, I'm Jim. Here's the MD5 of my password. An eavesdropper overhears that. Later on, the Kerberos avoids this problem. But if we weren't using any sophistication at all, an eavesdropper could not know my password, but he could convince somebody that he knew my password just by telling him, here's the MD5 of my password that he overheard. So he can do a replay attack. The replay attack doesn't have to understand what E1 is. He just needs to remember it and use it when anybody asks you for, well, what's the MD5 of your password? You know, oh, here it is. Yeah. Well, clearly we're not going to be able to allow that. So let's just take the password, add a random number to it, and never use the same random number twice, and take the MD5 of that, or the hash of that. So server sends a random number as a challenge, never uses the same random number twice. He doesn't even have to prove that he never gets twice. Excuse me. That will thwart the replay attack. Because if you tried to log in, I would say, for this random number 17, what's the hash of your password plus append 17 to the end of it? And if you didn't know what my password was, then you couldn't append 17 to the end of it, and you wouldn't be able to successfully succeed that. Right? So the next thing the Black Cats are going to do is a man-in-the-middle attack. You pretend to be Alice to Bob, pretend to be Bob to Alice. Now, if you convince Alice and Bob that your destination, your IP address, is the IP address of the one they want to talk to, then one of them is going to send you a challenge. You don't know the answer, but you take that challenge and you send it on to the other person. They'll give you the answer. So you take the answer. Okay, well, my password with 17 appended to the end of it, and you don't even know what the password is. But you do know that the MD5 of
E2.
Yes, E2 is, and now you can tell the Alice that what Bob said in response to the challenge when you passed the challenge along. The man in the middle. Now we're going to append the IP address or something that would prevent the message from getting to the right place, something that will thwart the man in the middle attack. And once we've done that, to be honest, we've gotten most of the pretty obvious attacks taken care of. Those are the things we talk about in network security based on the things that we learned in discrete math and based on the things that we worked on in the courses that are prerequisites. I apologize that some of the puns were abominable.
A-bomb in A-ball.
Yes, A-bomb in A-ball. If you're intrigued, take the course.
Thank you very much.
I don't know if I finished that in 52 minutes or not. The definition of a professor is someone who can tirade on any obscure subject for 52 minutes and then stop.
Ah, I apologize for the digressions that I inspired, but thank you very much.
They were fun.